Hold on, a few more joining now. Let me approve them first. All right, so could you please confirm if you can see the slide on the screen?
Yes, doctor.
Thank you. So after finishing the PN junction under thermal equilibrium, we started discussing about bias condition yesterday, and when we discuss about bias, there can be three different biasing conditions. So the first one is when you apply zero bias, or essentially it is a thermal equilibrium condition. Okay, so this zero bias here is basically your thermal equilibrium condition, just like what you have under typical thermal equilibrium. And the second condition is when you forward biasing the PN junction, and this is achieved when you connect the positive terminal of your circuit to the p-type and negative terminal of your circuit to the n-type, and you apply some voltage VA or VF, for example, and that will reduce the barrier height formed during thermal equilibrium condition. And your if you can see here, and if you can compare with the zero biasing, your barrier height will then be given by Q VBI minus applied bias voltage, right? So VBI minus VA will essentially form your new voltage, and when you times that with Q, you're going to get your barrier height. And the other condition is called reverse biasing, when you connect your negative terminal to the p-type, to the positive charge, and a negative terminal, positive terminal to the n-type, right? So you are connecting the opposite polarities together. And what it will do to your junction is when you apply the bias voltage, you can differentiate this by saying VR, and you can differentiate this by saying VF, so that you know that this is forward, this is reverse. And then your barrier height will then be enhanced, will be increased, and you're going to have your barrier height to be equal to Q times the product of VBI plus VR or VA. Okay, so you're going to get more. If in the perspective of carrier movement, for example, we have discussed that under thermal equilibrium condition, the carriers are no longer allowed to move because of the presence of the barrier in the middle of the PN junction, and this is reduced. The barrier height, when the barrier height is reduced under forward biasing condition, the carriers can now move when the applied voltage is enough to induce the movement of the carrier. So at this point, you're going to have a diffusion of your okay, cannot. Hold on, yeah. Now is it okay? The line here at my iNOS office is not So good. Now, okay, right. So the line here at Bukit Jambul is fluctuating sometimes. So let me just share again. Sorry for that. Let me share again the content. Can you see the slide on the screen? Okay, thanks. Right. So you won't have carrier movement or carrier diffusion in the reverse bias condition as well. So it's even harder for them to move across the junction under reverse biasing condition. Okay. So when you talk about the biasing condition, there are a few things that you have to understand. The first thing is how do you form the connection from the circuit to the semiconductor material or to the PN semiconductor materials in order to induce either forward biasing or reverse biasing. And then you should be able to draw the band diagram under three different conditions, zero biasing or at TE versus forward biasing and versus reverse biasing, right? So make sure you know how to sketch all the conditions with the corresponding EC, EV, EF on both sides, the barrier height for all the cases. Right. The electric field across the PN junction with an applied bias is given by this equation. You can just replace the values that we have in the question, for example, in this equation. So it's given by 2q over epsilon. We have discussed yesterday in the group permittivity of the material, and times the product of your VBI minus VA. So VBI here is the VBI minus VA. Oh, sorry. So here is VBI, yeah, VBI minus VA. So VBI minus VA. So that's basically the new level of the very high. So times 1 over the product of 1, the summation of, not the product, the summation of 1 over NA plus 1 over ND. Okay, so that will give you the electric field under this biasing condition. And the width of your depletion region is given by this Ln plus Lp. You can also write this as Xn plus Xp as what we discussed yesterday. So it's actually the same thing, but since it's from different sources, that's why some use X, some use L. L is to denote the width, right? So then the rest of the parameters are usually given, okay? So you can relate this equation of your depletion region width of both sides with the one that we discussed yesterday on the space charge region on both sides. So, right, okay. So this is the space charge region, if you like. Space SCR, right? SCR is space charge region or depletion region, sama. So, and that's given by this. Okay. So how do we then have the currents flow through the device? Okay. So previously we've done a calculation on the carrier distribution at thermal equilibrium. So this means the diffusion of carriers across the junction at thermal equilibrium. And we have already discussed about the PP naught, PN naught, NP naught, and N naught, right? So at thermal equilibrium condition, which is denoted by the naught. So now what happens when you have a forward bias voltage applied? Okay, so we know that when you have a forward bias applied, your barrier height will be reduced, and that will be given by your Q VBI minus VA. Okay, A here is the applied voltage. Huh? That's why you see it's used in forward biasing and also reverse biasing. But if you want to distinguish the voltage, you can just write as VF or and VR. Okay, forward and reverse. So now we are interested to know what is then the minority carriers that we're going to generate in the opposite region. Okay, sebelum ni kita discuss on PP naught in the P side, and therefore PN naught in the N side. Okay, majority whole carrier concentration of holes in the P side, which is equal to Na, or the original doping level. And then we already know how to calculate the PN naught, right? PN naught is the carrier density or density of hole in the N side at thermal equilibrium. So upon the diffusion process. Now we are interested to know what happens to the PP, no longer not, because it's now no longer at thermal equilibrium. It's now under forward biasing condition. Okay, forward bias, or it can also be reverse bias if you like, right? So, and therefore, the minority carrier concentration on the other side, in the P side, will be PNB. Okay, A and B here is the width of the depletion region, or the edge of the depletion region. So you can equate this to the SCR ataupun depletion region. So if you want to put the fixed charges, for example, kalau you nak letak fixed charges, you nak imagine fixed charges. So since the left hand side is the P side, so what polarity of the fixed charges do we have in this region? What polarity do we have? Now we're talking about fixed ion charges in the P side. What is the polarity? Negative, right? Good. Negative is the inverse of the original charge of the material. Sebab dia hilang hole kan, so it's going to be negatively charged, and therefore this one is in the n-type, losing electron is going to be positively charged. They are fixed ion charges, bukan mobile, fixed ion charges. So you can draw it like this as well if you want to imagine, if you want to put where is the SCR or depletion region into the picture. So now we're interested to know what happens at the edge of depletion region, which we label as PNB. So maksudnya concentration of holes in the N side at point B. At point B, So you want to know here at this point. Okay, and the same is also true for NN. NN is the original carrier concentration in the N-type, and under forward biasing, we are interested to know about NPA, density of electrons on the P side at point A. Okay, so that's why you have to label A and B first before you can label this minority carrier concentration, right? So let's have a look at how do we actually do the calculation next. Okay, so before that, just bear in mind, or just understand this one first. It's no longer not. Okay, kalau you letak not in your calculation, then it's automatically wrong because it's not under thermal equilibrium condition. So let's review a few things before you get to the equation. If you review drift and diffusion current across depletion region at thermal equilibrium, then we can make a few useful assumptions. At thermal equilibrium, there's no net carrier flow, neither electrons or holes. The reason is that the Fermi level is constant throughout the device, and hence there is no driving force for carrier to flow. So we've discussed that at thermal equilibrium condition, we have got only a single EF, and therefore there's no driving force for the carrier to flow across the junction. Okay. From the superposition model, we can assume that the drift and diffusion component, we have learned about both drift and diffusion of both carriers in the depletion region are equal but of opposite interaction. Equal value but opposite interaction. And therefore, if you talk about diffusion, current density associated with holes, remember the current density of a carrier in this particular condition is given by the summation of your drift component and your diffusion component. So drift component is given by Q mu H P times electric field minus, or because of the negative sign of the diffusion current for holes, minus Q times diffusivity times dpdx, and that equals to 0. So that means they are equal value but opposite in direction, and therefore you can say that your drift component is equal to your diffusion component for the holes. So note that this assumes that at zero bias there are large drift and diffusion current across the junction, which is not true, but the outcome J equals 0 is predicted correctly. So this is the net is always 0. Okay. So let's have a look at the calculation of both minority carrier concentration. So we have discussed about the PP and PNB, NN, and NPA. Okay, and note that the A and B is the edge of the diffusion region on the P side, which is point A, and on the N side, which is point B. Okay, at forward bias condition, both drift and diffusion currents are large and opposing in the depletion region. So remember, this is your depletion region. At moderate bias, the net current flow is a small difference between these two much larger values. So it can be approximated as equal. So so let's have a look at the PNB calculation, right? PNB calculation. So how do we then you started off with PP, and this PP is equal to NA on the P side, and under certain biasing condition, under a forward biasing condition, this PP is going to end up as PNB in N side at point B. Okay, so that's why you should be able to describe the three things. Remember, I told you last time, PP naught, NP naught. So make sure you know the three things, because the three things still come again as PNB or NPA in this case. So the PNB here is given by your PPA. Your PPA, where's your PPA? That means this is your PP at point A, which is essentially your PP or your NA, sama. Exponential of negative Q times VBI over KT times exponential of QVA. VA is your applied bias over KT. So this is how your applied bias affects the minority carrier concentration at point B. Okay. So we're going to see later on. So we will see how the magnitude changes graphically next. So PPA in this equation can be approximated as PPA equals to, PPA equals to PP naught. Kenapa dia jadi macam ni? So yeah, let me just... Okay, can you see the slide? Just in case.
Yes, sir.
Okay, right. So your PPA is given by PP is equal to PP naught. Your PPA ni sama dengan PP naught. There's no change because you are still within the P region and not yet crossing the SCR. Okay, and that's given by your Pn naught, if you want to know, Pn naught exponential by Q VBI over KT, but it's going to be equal to your Na. So let's see what happens to your PNB and NPA. Okay, PNB and NPA, sini ya. So we're going to look at this and this. How do we then calculate that? How do we simplify that? So your PNB, that means your hole in the n-type at point B, PNB, NPA. So let me just do this so that it's clearer to you. PP, NN, okay, this is point B, this is point A, PNB and PA. So your PNB here, the density of holes in n-type at point B is given by your Pn naught. So what is this Pn naught? Let's recall what is this Pn naught. Anyone? Apa maksud PN0? Sekarang kita nak kira PNB ya. In relation to PN0. What is PN0? Okay, holes in n-type at thermal equilibrium, right? So when you want to calculate the PNB is the holes in n-type at point B under forward bias condition. So you want to compare that with holes in n-type at thermal equilibrium. Maksudnya kita nak tengok how much changes do you have for hole as the minority carrier in n-type at forward bias condition in comparison to thermal equilibrium. Okay, kita tahu bahawa sebelum ni we have done this curve as well. At thermal equilibrium. So kita tahu this is the minority carrier at thermal equilibrium. So you want to know now how much is the change that you're going to have if you apply the bias. But yesterday we have discussed that when you apply forward biasing, at some point you expect the carriers to cross again, isn't it? Expect the carriers to start diffusing again across the junction, and therefore we expect the minority carriers on the other side and electrons in p-type, holes in n-type to be higher than the thermal equilibrium condition. Sebab sekarang kita dah, by reducing the barrier height, you are forcing the diffusion of the carriers from both sides into the opposite region, and therefore you should expect higher level of minority carriers to be found in the opposite region. Okay, so that's why we need to see the comparison between this in relation to this, in comparison to this. So therefore your PNB is given by PN0, your minority carrier concentration at thermal equilibrium condition, times exponential component that will drive the diffusion of your carriers into the opposite region. So this exponential component will drive the diffusion of your carriers, electrons into p-type, holes into n-type. And that is a function of your applied voltage. Okay, so PNB equals to PN0 times exponential of QVBA over KT, and that is also equal to Ni squared over Nd. Ni squared over Nd is your PN0. Okay, remember law of mass action. So kalau you have not calculated that, so you can either calculate PN0 first before inserting into this equation, or you can just do the calculation here, Ni squared over Nd, exponential of your bias voltage component. Okay, and the same thing happens to your NPA as well. So we want to know how much NPA changes in comparison to your NP0. Okay, so because at forward biasing condition, you should expect more carriers to cross the junction, and therefore you're going to find more minority carriers on the other side, and that's given by NP0 exponential of negative Q VBA over KT. Okay, and your NP0 here is given by Ni squared over Na. Okay, just the opposite of the above, and times exponential component of your applied voltage. So you can imagine this graphically. You can translate that graphically into this. So for example, if you plot if you plot your log concentration on the y against distance on the x, and this is your depletion region width A and B on both sides, you can then say that with applied biasing, by increasing the applied bias condition, and you will effectively reduce the barrier height and forcing the diffusion of carriers into the opposite region, then you should expect at thermal equilibrium condition, it could be here, for example, the level of carriers. And when you apply your forward biasing, you could probably find a higher level of minority carriers at the same point. Okay, due to the exponential component in the equation. Okay, so hole density on the other side of the junction, that is at edge of depletion region, depends exponentially on applied voltage VA, and the same happens to the electron as well. So this increase of hole density in the n-type, which is a minority carrier, hole in n-type, or increase of electron density in the p-type is known as carrier injection. So remember last time we talked about carrier injection when we discussed about the equation of n equals to n naught plus delta n and p equals to p naught plus delta p. This is a very generic representation of carrier injection, where your carrier injection is given by this delta component. And the same thing happened here because you are now injecting carriers across the junction, and this is known as carrier injection as well. And this is activated or induced by applied bias in forward direction. Okay. So that's one thing. You want to know how much changes do you have across the depletion region. Okay, so that's one thing. But bear in mind that when you talk about PN junction or device, eventually we are talking about the whole piece of PN material, isn't it? So this is only in the central region, the depletion region or SCR. So we are now only talking about the concentration of the carriers at the end of the depletion region, but it's still in the central part. So we've done the calculation yesterday, and it shows like with 10 to the 15 and 10 to the 16, we're going to have the depletion region width to be somewhere around 0.95 micron out of the whole 400 micron, for example. So if you want to talk about the actual devices, your actual devices, saya ambil silicon. So to put this into perspective so that you can appreciate, because now all the things that we've done is really abstract. Tak nampak sangat. You have to put that into into perspective all the time. So this is a silicon wafer, for example, and this is my solar cell. One example of semiconductor devices that you may have. You can also apply this to detectors or some other devices that use the same principle. So now I'm talking about this whole thickness of 180 microns. So that means if you want to transfer my dimension into the sketch, so this whole thing is 180 micron. And this SCR is only like less than 1 micron. So it sits somewhere in between, only 1 micron out of 180 microns. So 1 of 200, 1 over 200 in terms of the thickness, if you like, close to. And we have only discussed about the minority carriers under biasing condition at the edge of the depletion regions. That means we are only talking about this 1 micron region. And we have not yet discussed about the remaining 179 micron minus sini plus sini. We still have like 179 micron to think about, right? So now we've only discussed about this 1 micron somewhere dekat surface, close to, because junction is typically formed near the surface. It cannot be so deep. You cannot have like a junction of 50 micron into your silicon. That's just too deep and won't work. So your typical junction depth is about 1 micron or less. So we call that junction depth, the depth of the junction into the surface. So what happens to the minority carriers then within this 179 micron? So that is the next thing that you have to learn, which is what happened. How does the whole or minority carrier density vary across the entire region? What happened here? Before you put on your contact, because if you look at my sample here, kita ada contact. This is you can see the bus bar here. So this is a silver metal contact, silver contact. You can only see this vertical part, but there's also horizontal line, very small horizontal line you cannot see, but they are there, very small. But the big one is called bus bar, but the horizontal one is called metal fingers, very small. And this is on the end side. This is on the end side, so that means the contact yang saya draw belah kanan ni on the end side. And on the P side, you also have the other contact. So belakang ni ada juga contact. You can see that, right? Those bars. So those are aluminium contact. So kalau nak translate this so that you understand for my sample. So So we have only discussed up to this point the HO depletion region, but if you want to know what happens to the carriers across, you need to learn this, because eventually if you want to extract carriers at the metal contact, the carriers still need to travel across more than 100 micron to the left and to the right to be able to reach the contact. Barulah dia keluar and complete the circuit. Okay, kalau selagi mana dia tak keluar, so that means you may have your carriers increase here, but then if they recombine somewhere here, habis, gone. Your carriers cannot be extracted. Okay, so maknanya you don't want to have a combination there across the volume of the neutral part of both sides. Okay, selagi dia tak keluar kat metal contact, selagi tu dia tak selamat, if you like, right? So that's the thing. So this region, beyond the depletion region, beyond the depletion region, to the left and to the right is called quasi-neutral region. Okay. So you have depletion region here. Depletion region, I put AW, depletion region. So to the left and to the right is where you have neutral region. So remember last time we talked about the plot of your space charge. Kita ada space charge dekat center je. So to the right and to the left is essentially neutral. And this is called QNR, quasi-neutral region. Quasi-neutral region. So beyond this, there's quasi-neutral region. Okay. So we assume that this region is uniformly doped. That's why you're gonna get your profile like that, because it's uniformly doped, and the same is applicable for the other side as well. We assume this to be uniformly doped, right? Beyond depletion region. Okay. So to solve this, and also the current density in the p-type, we need to define new axis. So you have to go into the QNR. Okay. So we should expect diffusion down a concentration gradient as well. You have done this calculation where it's given by your Vn naught exponential of a QVVA over KT, and we should expect further diffusion of the carriers across this region, across this QNR. Okay. So is it okay so far? Can you understand, or there's something that you don't understand at this point before we move on? Do you understand how do we get the minority carriers under biasing condition in comparison to the thermal equilibrium condition? How does the minority carriers increase in comparison to the thermal equilibrium condition on both sides? Okay, so let me ask a question before I proceed, yeah, so that I can make sure that everyone understands. All right. Fatin, can you explain a little bit how come your minority carriers increase when you apply forward bias? Will you explain?
Forward bias
Yes.
put the minority carriers from the neutral part into the from the neutral material. Let's say hole from P type, it will diffuse through the junction and go to the opposite material, which is the N type.
Okay. Then why is it increased if you compare to thermal equilibrium condition? If you compare in terms of minority carriers? You get it already, diffusion, but then why is it higher than the minority carriers at thermal equilibrium condition?
I'm not quite sure, doctor, about that.
Okay, all right, no worries, Fatin. So anyone would like to assist on that? Mariam? Mariam, what do you think? Why the minority carrier concentration increases when you apply forward biasing in comparison to thermal equilibrium condition? Mariam ada? Shazanani? Shazanani? Why do you have higher minority carriers under applied bias condition? Can I mute yourself? 9:40. Let's go for another 10 minutes. Ada? Anyone? Shasha? Shasha tak pernah dengar suara ni. Shasha? You there? I want to make sure everyone understands first before we continue. Okay, let me see here. Applied voltage, yep, okay. You have the applied voltage and therefore, Shadani, so when you have the applied voltage, what happens next? Why does it lead to increased minority carriers? What has stopped the carriers to flow at the molecular condition? What has stopped the carriers to flow at thermal equilibrium condition before this? Anyone? Apa yang menyebabkan carrier stop moving at thermal equilibrium condition? Anyone? Kenapa carrier stop? The depletion region are not quite. Is a contribution from depletion region, but what exactly stops the carriers?
The VBI that is formed from the depletion region due to the positive and negative static ions, doctor.
Yeah, it's the barrier height, right? It's the barrier height, which is determined by, or which is dependent on your VBI. Okay, so essentially it's Q VBI. That is the barrier height formed at the junction in the SCR in the depletion region. So it's not the depletion region itself, but it's from the depletion region. But it's due to the barrier height. So what if you want to relate this to what happens next to when the minority carriers under applied bias condition, forward bias, you have to go back to the barrier height before you can start telling stories about what happens next. So when you apply the forward bias, what happens to the barrier height? The barrier height reduces, and therefore what happens? What are the following keywords that you should have? The barrier height reduces, is the first thing, and therefore as a result, we should expect what to happen? Further diffusion, right? Further diffusion of carriers from both sides into both sides. And therefore, as a result, what should we expect at the end of the opposite depletion region? gambar dah ada dah kat bawah ni. What should we expect? The barrier height is reduced, further diffusion takes place. As a result, more minority carriers crossing the junction and reaching the other side of the diffusion region. Okay, that's how you should tell if you're asked about what causes the minority carriers to increase under forward biasing condition. Okay, ini baru dalam diffusion region. So we have not discussed about the quasi-neutral region yet. Okay, it's going to be a bit more complicated as well. So in the quasi-neutral region, let's go on for the next few minutes. From the continued equation, we have for n-type region, the generation rate is we can have the carriers by having minusing the generation rate with the recombination rate. Generation rate minus net recombination rate. So you can imagine the profile of the minority carriers to be following this on the right. This on the right. Okay. So this is the SCR. So tadi kita discuss tentang ni. If you want to relate back to the previous case, we have been discussing about this. Kat sini, going forward up to this point. Okay. And also we have been discussing about this. Kat sini, go down up to this point. Sekarang kita nak tengok what happens into Q and R. What happens into Q and R. Right, further into the material before the carriers reach the contact on the interfaces on both sides. So you can imagine the profile to be an exponential profile like this, which is essentially a continuation of what we've got in the previous case in the depletion region on both sides. Okay, and the profile on the P side, left side, will be given by NPX. Okay, NPX. NPX here means concentration of electrons in the p side at point X. Okay, and it should be higher than the level of NP naught. NP naught being at thermal equilibrium without any biasing condition. And the same goes to N side as well. And you're interested to know the minority carrier with profile of P and X. Okay, which is whole concentration in n-type at point X, which is expected to be higher than P and naught due to the biasing condition. Okay, and the equation, for example, if you want to talk about the general solution, we're going to see this one later on, is going to be given by this equation. Delta P is equal to A times exponential of X, the point X, over LH. This is the L that we're going to talk about. Remember, we have discussed about diffusion length, and this is where the diffusion length comes in. Diffusion length of both sides, okay? So let's see about this. So diffusion length will be determining the performance of your device eventually, okay? So if you can recall, the diffusion length is the distance traveled by the carriers from the point of generation until the point of recombination. So that means along the way, when it's traveling across the quasi-neutral region, there is internet problem. Can you hear me? Okay. Can you hear me now? Okay. Tadi ada
Doctor, your line is really bad.
It looks okay on my Wi-Fi, but I'm not sure whether you can hear me now. Can you?
Now it's fine, Doctor.
Okay, okay then. Okay, let's just finish it off. I think it's a sign of stopping, perhaps. Okay, let me just finish off this slide, okay? Uh, so your PNX given by your PN naught plus PN naught times exponential component. Not only that, but you also have to include the diffusion length component into this equation, and that's given by E to the power of negative X over LH, right? Diffusion length in the N-type material. Okay, kenapa dia LH? Why is it LH here for P and X? Why is it LH? Why is it not? Why is it not LE? Kenapa dia LH? Anyone? Now we're talking about this side. Why is it LH that we are concerned about? Any idea?
Is it the diffusion length of holes in the N-type?
Yes, but why is it hole? Why is it not electrons?
The minority carrier in the N-type.
Yes, exactly. Good. Yeah, Fatin said minority carrier. So remember, we are talking about minority carrier. Minority carrier from the injection. Okay, from the injection. Kenapa kita cakap tentang minority carrier from earlier on? Why we are interested in minority carrier, not majority carriers? Can you recap? Kenapa kita last few lectures? Why are we so interested in minority carriers in this case? Why not majority carriers? Anyone can tell something about that?
Is it because for carrier injection, there's more significant change for the minority than the majority carrier?
Exactly, right? So we discussed in a couple last lectures on the minority injection, right? So it barely changes the majority carriers, but it significantly changes the minority carriers. So that's why we interested.
Doctor, you got cut off again.
Sekarang okay tak? Boleh dengar ke? Right, so let's just wrap it up lah. So we are interested in the minority carriers. I don't change the slide. I don't share the slides anymore. Let's just finish it off. So we are interested in the minority carriers. So that's why when you're talking about on the right hand side PNX, you need to couple that with diffusion length of your holes, because hole is the minority carriers in N type. And the same goes for your NPX on the left. You're gonna factor that with LE, diffusion length of electrons, because electron is a minority carriers in P type. Okay, so kita nak tengok macam mana minority carriers survive in the opposite region. So they are devices. If you go back to the big picture, they